In this lesson, we finished the source transformation sequence with two compact examples. The key idea is still terminal equivalence. A voltage source in series with a resistor and a current source in parallel with the same resistor can describe the same behavior at the two outside terminals. That is why we can replace a complicated block by a cleaner equivalent block, as long as we preserve the correct voltage, current direction, resistance, and polarity. In the first example, the source is dependent, so its value contains IA. That is allowed. We transform it symbolically and solve for IA at the end. Example 3 asks for the current IA. The current IA is the current through the 3 ohm resistor, moving from the 10-volt source toward the right. The middle branch has 6 ohms to ground. On the right, an 8 ohm resistor is in parallel with a dependent current source of value 2IA. This dependent current source points from left to right, and it is followed by a 4 ohm branch to ground. The important note is that a dependent source does not prevent source transformation. Its value just remains symbolic. Transform the dependent current source in parallel with 8 ohms into a dependent voltage source. The value is 2IA times 8 ohms equal to 16 IA volts. The 8 ohm resistor is then in series with the 4 ohm resistor, so that side is 12 ohms. Converting that series pair back to Norton gives a current source of 16 IA divided by 12 in parallel with 12 ohms. Now 6 ohms in parallel with 12 ohms gives 4 ohms. After one more transformation, the circuit is a single loop with 3 ohms plus 4 ohms, so 7 ohms total, and a dependent source of 16 IA over 3 volts. KVL gives 10 volts plus 16 IA over 3 equals 7 IA. Multiplying by 3 gives 30 plus 16 IA equals 21 IA. Therefore, 5 IA equals 30 and IA equals 6 amperes. Example 4 asks for V0 in a longer circuit. We are also given that the current through the bottom output branch is 5 over 2 amperes to the left. The reduction is a chain of small transformations. The left 2 amp current source, in parallel with 16 ohms, becomes a 32 volt source in series with 16 ohms. That source combines with the 8 volt source, leaving a net 24 volt source and 36 ohms on the left side. On the right side, the 6 ohm and 3 ohm resistors are in parallel, giving 2 ohms. With the 10 ohm resistor, that becomes 12 ohms. Continue reducing example 4. The 24 volt source in series with 36 ohms becomes a current source of 24 over 36 or 2 over 3 amperes in parallel with 36 ohms. That 36 ohm resistor is in parallel with 12 ohms, so the result is 9 ohms. Transform the 2 over 3 amp source in parallel with 9 ohms into a 6 volt source in series with 9 ohms. The 3 amp source and the 12 ohm equivalent give a 36 volt source in the same series path. At the end, the loop resistance is 9 plus 12 plus 7, which is 28 ohms. The given current is 5 over 2 amperes, so the total resistor drop is 28 times 5 over 2, equal to 70 volts. The sources contribute 6 volts plus 36 volts plus V0, so 42 plus V0 equals 70. Therefore, V0 equals 28 volts. The two examples show the same discipline. First, transform only pairs that are truly series or truly parallel. Second, combine resistors before doing another transformation. Third, keep dependent source values as algebraic symbols instead of replacing them by numbers too early. Finally, do the last equation carefully. For example 3, the final equation is 10 plus 16 IA over 3 equals 7 IA, giving IA equals 6 amperes. For example 4, the final equation is 42 plus V0 equals 70, giving V0 equals 28 volts.